Hello, everyone. Can you hear me? Yeah. Very good. Right. Well, welcome to Reinventing the Transaction Script. Probably the most boring title I've ever done as a talk title. It's after lunch, and it sounds like a really boring talk. I hope the talk is not as boring as the title sounds. So, I'm Scott Wlaschin. I have a website, F# for Fun and Profit, which is about F# and about fun and profit. So I do a lot of functional programming, and that's part of the theme of this talk. And what triggered me to do this talk in the first place is when I started seeing people say that transaction scripts are a bad thing. Now, if you don't know what a transaction script is, I'm going to explain in a minute. But for people who came of age, 10, 15 years ago, this is one of the standard things, one of the standard patterns we had. And I see people say, it's not good enough for this, it's anemic, it's an anti-pattern, it's more of an anti-pattern with no sequel, etc. There's all these things that people say about them. I think people have a misunderstanding of what they're good for. So I think they are not a bad thing. In fact, they are an excellent thing. And I hope to persuade you that they really are a very good way of thinking about solving problems. So, what is a transaction script? This term was created or popularized by Martin Fowler in his book, Patterns of Enterprise Application Architecture, PEAA, it's normally called, and it came out in 2002. And this was people who were programming back then, like old people like me. This is one of our Bibles, and we religiously followed all the patterns in this book. And one of the questions he asked in that book is, how do you organize your domain logic? Where, should you put it here? Should you split it around? How should you do it? And so one of the patterns for this was a transaction script. And the idea is that most business applications you can think of as a series of transactions. And so a transaction script is basically all the logic you need to do a transaction is in one single procedure. And he uses the word procedure, so that's how old it is. And then if you need to do database stuff, you just literally put the SQL statements in line, or you have a very thin wrapper or something. But basically everything you need in one place. And each business transaction has its own transaction script. So that's pretty straightforward, that's pretty easy. And he had some other patterns in there too. He had the transaction script pattern, he had the table module pattern, which is really not so trendy right now, the domain model, which is now very popular, obviously, domain-driven design and so on. And the idea of that is you have an object model, and for all the different bits of domain logic, you have a class that specializes in that particular piece of domain logic. You have a customer class and a product class and a whatever class, And the behavior and data are kept together. It's object-oriented. And then you also have services. He also mentioned service-layered architecture in this book, with services and application services and domain services and all that other stuff. So these are the patterns that were in the book. And since domain logic is a really important part of your code, people paid a lot of attention to these patterns. And of course, people have very strong opinions about these patterns. And the transaction script was considered like too simple, it's too anemic. Table module is too database-centric. But domain model and services and layers are good because they're complex, nice and complex. Complex is good, right? And it's just interesting to me that simplicity is considered sort of a bad thing. And I just want to have a little side note here about developers and the way they think about things. If you have a scale from simple to complex, we really do think of simple things as boring and complex things as awesome and interesting. And all I have to say, is microservices and Kubernetes and event sourcing, and you can think of all the things which are complex. Now, it doesn't mean they're a bad thing. Sometimes you need the complexity, but we jump onto the complexity. We think complexity equals good, and simple and boring equals bad. And, Visual Basic and PHP and stuff are bad because they're too simple. It's too easy to get stuff done. You need to have a framework, So transaction scripts have a bad reputation. If you were around in those days, or if you've read the book, people think transaction scripts are like for people who are stuck in the 90s and you're doing a lot of Java, or maybe you're even using COBOL, because basically all COBOL stuff is transaction scripts, right? It's just like mainframe stuff. So it's very uncool. If you use transaction scripts, you're an uncool person. So I'm going to try and tell you the revelation that transaction scripts are actually very cool because you can use functional programming. If you reinvent them with functional programming, it's very cool because functional programming is cool. So functional program-based transaction scripts are super hipster and super cool, and then they're okay. So, all right, so let's look at the pros and cons of transaction scripts. A typical transaction script, gets some data from database, does some business logic, writes some data, gets some more business logic. Maybe there's a little branch on some condition, and it does some more database, some more business logic, etc., etc., etc. And again, this is how most code used to be written before object-oriented philosophy came along. But what's interesting about this is actually really easy to understand. It's like one thing after another. It's one directional data flow. It's really easy to understand what's going on. So that's good. I mean, it's all in one place. It's all focused on what's important, right? You don't need to have a Yagni reminder because there's nothing, you're not building a framework, you're building something that delivers some particular piece of value. So everything in this script is relevant to this script. There's no interface that has methods that you're not using in the script because there are no interfaces, right? So it's very, very specific, it's very relevant. That makes it also easy to understand. Now on the flip side, it's hard to modify. If you add new conditions and you want to try and evolve this thing, you add more conditions, and you end up with a tangled mess of logic sometimes. That's not good. And I think, as Martin Fowler said, there's no graceful path to richer behavior. Like, at some point, most people just throw these away and create a rich domain model. Or often you just copy and paste the whole script and make your changes and then leave the original script alone so you don't break it, that kind of thing. So that's why they have a bad reputation. And there's no rich domain model. We're literally reading things from the database, doing some logic, writing stuff out of the database. So all the stuff about domain-driven design and having objects with behavior and stuff, that all goes out the window. This is, like I say, it's very 50s mainframe style. So if I want to take this piece of code and reuse it for some other script, it's really hard to do because it's not designed to be modular. And it's also really hard to test because the business logic and the database logic, are all mixed up. Here's the business logic, here's the database logic. They're all tangled together. That makes it really hard to test. Trying to write a unit test for this bit or a unit test for that bit is going to be really hard. So you can't just test individual bits on their own. So those are the problems. Can we fix these problems? Yes, we can. And that's what this talk is all about. And the answer, of course, is to use functional programming, which is cool, and domain-driven design is cool. And so we get a very high coolness score by doing this new reinvented transaction script. And it's all about being cool. Right, so let's talk about functional programming. I'm sure most of you are familiar with functional programming by now, but I'm just going to give you a little intro, kind of my way of thinking about it, without the jargon. So here's a function, and I like to use the railway track analogy a lot. You'll see it in all my talks. A function is something, this little bit of railway track, it has a little tunnel, a tunnel of transformation, I call it. And so something goes into this tunnel, and it comes out different. So an apple goes into this tunnel, and it turns into banana, right? So it's an apple to banana function. So that's it. That's all a function is. It's really simple. If you've played with a toy, like a Brio wooden railway set, that's, you know how this works. But here's the key thing about functions, is they are standalone things. They are not attached to a class. They're not attached to anything. They are, they don't use global variables. If you need extra parameters, you pass in extra parameters. They're all completely independent. So standalone is another word for reusable. So because they're standalone, they are much, much more reusable than things that aren't standalone. And also because they're standalone, you can use them just like you use a string or an int or a date or anything. They're just values that you can pass around. So for example, here is a function which has a normal input, but has another function as an output. Or here is a function which has a function as an input and a normal thing as an output. And here is a function which has a normal thing input and a normal thing output. But you can have another parameter which is another function that you pass in, which controls how the main function works. And that controlling another function, that's the strategy pattern right there. So in functional programming, the strategy pattern is literally just passing in a function as another parameter. So that's it. That really is, in my world, that's everything you need to know about functional programming. Seriously. That's the foundation. Now, you can get really, really complicated. You can have a function that returns another function that's a factory for other functions that has parameters. I mean, it can get really, really complicated, but the core principle is that is really it. And everything that comes out of that, things like monads and all that stuff, is just a kind of follow-on to this. Right, so the core functional programming principle is composition everywhere. Functional programmers love to do composition. That's their main thing. So what is composition? Everyone knows what composition is because hopefully you've all played with Lego, right? Now, Lego has a philosophy behind it. There is actually a Lego philosophy. First of all the pieces are designed to be connected, and the pieces are reusable pieces. And if you connect any two Lego pieces together, you get another kind of piece that you can keep connecting to, right? You don't have to stop at some point because you run out of bits to add things on. Every Lego bit can be added onto. So here's some Lego, and you notice that every single Lego piece has the little bumps on it. They're all designed to be connected. That's a key part of Lego. If it didn't have that, it wouldn't be Lego. And here it's really obvious. You can build something, and you can take it apart and build something else, right? So that only works because there are no strings attached. Literally, there are no strings attached to Lego pieces. If they had little wires or something coming out of them, it would be really much harder to build things out of them. And here's the composition. You can connect two pieces of Lego to make a bigger thing, connect that to make a bigger thing, connect that to make a bigger thing, and so on and so forth. You do not need a special adapter. At no point do you have to stop and say, I can't continue because I need a special adapter that you can always keep going, right? You can just adding and adding and adding, which means you can start from really small things and make really big things like that. So this is a very cool piece of Lego. This is a piece of Lego, and because of that, you could take two of these and connect them together to make an even bigger one, right? Because they still have little bumps on it. So that's what I call the power of composition. Composition is a great way to build big things from smaller things. Right, so the functional programming idea of composition is the very same thing. So you have two different functions, and you want to connect them together to make a bigger function. And this is where the railway analogy is really nice, because it's really obvious. If it's bits of railway, how do I connect these two functions together? Well, I literally take the output of one and plug it into the input of the other, and now I have a new function. So that's before, and that's after. Now what's cool is this new function, you can't tell that was built from smaller functions. I mean, from your point of view, this is just a function that turns apples into cherries. And, where did the banana go? Right? The other function had bananas. There are no more bananas in this one. So the fact that you've got some sort of data hiding or abstraction going on, that the smaller pieces have to worry about the stuff, but the bigger pieces don't. But then this is just another function, and I could connect this to, if there's another function that consumed cherries as input and spat out pineapples or something, I could take this cherry emitting function and connect to that to make an even bigger function, right? So the fact that you're using the same techniques at different scales is really nice. So this composition is you can build big things from small things, composition all the way up. So here's a little example. Let's say you have a low-level operation like uppercasing a string, classic function. You have a string as input, you have a string as output. You take a bunch of these low-level operations and you make like a service, like an address validation service that takes an address as input and a validation result as output. And because I'm over 40, I'm going to use the word service. If you're under 40, you can use the word microservice. So you take all these services or microservices and you combine them to completely support a use case or a story, whatever you want to call it, like updating your profile data in the database. So you pass in some data and some stuff comes out. And you take all these use cases, and let's say you're making a web application. A web application is, in fact, a function. It has an input, which is a HTTP request, and it has an output, which is an HTTP response. So web applications are functions. And so typically inside this big function, there's some sort of branch, a controller or a dispatcher or a router, whatever you want to call it. Basically, based on what the input is, you call one of the other functions inside, and that's it. So that's functional composition from the ground up all the way to a big web app. So it's kind of fractal, self-similar. It's not quite fractal, but it sounds cool to call it fractal, so I'll call it that. So here's like the internals of a web app. Now, obviously, there's branching going on. There is, lots of little functions going on. But the big picture is still an input and an output. You literally can build bigger things from smaller things. And if you ask if you look at the functional programming web libraries, this is exactly how they do it. So I have a whole talk about the power of composition, also from NDC. One other thing I just want to point out, which I'll be mentioning later on, is that the arrows are all in the same direction. The arrows go from left to right. There are no loops, there are no cycles. That makes it easy to understand. Right, now, in statically typed functional programming, we have things called types. And types are just data, and they can be composed too. So let me explain how that works. In a language like F# or Haskell or Camel, we have what's called algebraic type systems. That's a bit of jargon. But if you replace the word algebraic with composable, that makes a lot more sense, and it's actually exactly what it is. So a composable type system, what does that mean? It means you can build bigger types from smaller types. That's what composition is, just like Lego. So in a composable type system, there are actually typically two ways to build a new type. One is to AND them together, whatever that means, and the other way is to OR them together. Now, I'm going to explain what that means in a second. But something to point out is that composition of types is only possible because in functional programming, data and behavior are kept separate. If you have the data and the behavior in the same thing, in an object, in object-oriented programming, it's really hard to do certain kinds of composition because when you combine two objects, which methods should belong to which objects and so on. So it just becomes tricky. But if it's just data, it's quite easy to do. So what do I mean by composing with AND? Well, just like when we use English and we talk about doing AND, when I say I want a fruit salad, and it's an apple and a banana and a cherry, there's the ingredients, I'm using the word AND, right? And this is what you might call a record type, or a tuple, or a pair, or a struct. This is a really, really common thing in any kind of programming language. So here is an F# version of this. We're saying a fruit salad is an apple and a banana and a cherry, because all the fields are required, right? It's got 3 fields. Every single field has to be filled in. Okay, so that's easy enough. Now, the other way of composing is with OR. And again, just like in English, we would say, if I want a snack, I have an apple or a banana or a cherry. So one of the 3 choices, not all at the same time, just one of the 3. And in F#, we use the vertical bar like this. So we say a snack is an apple or a banana or a cherry. You can think of this as like a glorified enum. You can think of it as like a snack class with 3 subclasses. Not quite like any of those, but that's the kind of idea behind it. It's a quick way of making a choice between different things. So I call these choice types. In F# they're actually called discriminated unions. You can also call them sum types, co-products if you fancy. Right, so let's look at how you actually build real stuff with, this sounds very nice in theory, but how do you actually use it in practice? So here is a real-world example of building a payment system. Let's say that you take 3 forms of payment. And let's say cash and PayPal and credit card, say. Now, for cash, you don't need any extra information. For PayPal, you need an email address, and for credit cards, you need a card type and a card number, an expiration date, and all that other stuff. So, how would you implement this, or how would you model this if you were going to write code to implement this requirement? So I think it depends on whether you're an OO person or a functional programmer. Now, if you're an OO person, you would probably implement it as some sort of abstract base class or an interface called a payment method, and you'd have all the other things kind of inherit from that interface, or implement that interface or inherit from that base class. So we have a cash class, we'd have a PayPal class, we'd have a card class. And I think most people would probably do it this way if you're an OO kind of person. So let me show you a different way. If you're not an OO person, let me show you a completely different way of doing this. So in functional programming or F#, I would probably build it up like this, building up a big thing from a bunch of small things, the composition way. So we start off by defining some primitives, because in domain modeling, real people do not use words like strings and floats. They use email addresses and card numbers. Now, they might be represented by a string, but that's not in the domain model. Those kinds of words should never exist. So we have a thing called an email address, we have a thing called a card number, which are our primitives. And then we say, well, a card type, that's a choice between a Visa and a MasterCard, so that's a vertical bar, an OR. And a credit card information is a card type and a card number, so that's an AND type or a record type. So we've got a choice using OR and a record using AND. Okay, so let's keep going. Let's build up something on top of that. Let's build our payment method now. So we said a payment method is cash or PayPal or credit card. So we say cash or PayPal or credit card. So it's a choice type. And for the different cases, there's different information to go along with each case. So in the cash case, there's no information needed. For the PayPal case, we need an email address, and for the credit card case, we need the credit card information. So that's a choice type. But we don't have to stop, because we can keep building and building. Just like with a Lego, you can keep adding and adding and adding. Right? The composition, you can just keep going. So let's keep going. Let's do some more stuff. Let's define a payment amount. And again, I'm not going to use the word decimal or float. I'm going to use payment amount. That's the word they use. Currency is, say, euros or dollars. So that's a choice. And then we can keep going. Say a payment is an amount and a currency and a method. So an and, that's a record type. So that's how you build a big domain for a bunch of small things. So we can keep going and going, but that's basically a way that you can build a big domain from a bunch of smaller types. So that's the composition in the type system. I think it's very, very cool. Right, so let's apply some of these functional programming principles to transaction scripts. So transaction script is a bit of a mouthful, so I'm going to call them workflows instead. So a workflow is some business operation that adds value to the business. Okay, now you could call it a transaction, you could call it a story, a use case, lots of different words for these things. But I'm just going to use the word workflow because it's kind of a neutral word. So workflows are triggered, something happens in the outside world, that triggers your workflow to happen. And typically the workflow, if it needs to tell somebody else that I did something, it emits some events at the other end saying, hey everybody, I just took payment for this order, now you can ship it or whatever. So that's how it communicates with the outside world. And these events, what triggers things and what comes out the other side, these events are actually the glue in a business. Like something happens that triggers some workflow, the workflow says, I just finished something, well that triggers something else, and then they say, I just finished something, that triggers something else. How the different business processes are connected by events is really, really important. And if you're not familiar with it, I would check out event storming as a process for determining what the business events are. It's a really excellent, it's kind of like a hyped up, agile way of getting everyone in the same room and discovering what these things are. So how do we implement these workflows? Well, we're going to implement it as a function, a little bit of railway track, right? So there's an input and an output. It maps really well to functions. And the inputs and the outputs are going to be modeled by these composable types. So when I say it takes in a payment method and it spits out a completed order or something, those things will be modeled by payment types. They're not going to be modeled by ints and strings. We're going to be modeling them with these nice composable types. Okay, so we're using everything we've learned about functional programming so far. So that's good. And the other nice thing about functions is because they're composable, it's really easy to build a bigger workflow from a bunch of smaller ones. And so, in a transaction script, in a classic transaction script, it's not at all modular. It's just one thing after another. But when you're doing functional programming, modularity is like built in. As I say, the functions are standalone. You almost can't help but have modularity. So it's really easy to build a workflow from a bunch of smaller pieces. And so you have these individual pieces, you glue them together to make a bigger piece, and that's your workflow. Because each of these components are standalone. Like I said, they're not attached to, they're not methods in a class. Because they're standalone, you can use them anywhere. So you could use them in different workflows, different anything you like, but they're completely standalone. Right, so let's talk about domain-driven design. For people who are not familiar with domain-driven design, it comes from this book by Eric Evans that was published just after PEAA, 2003. And his key insight is to focus on the domain and the domain logic rather than the technology. Developers love to talk about technology. The business does not care about technology. They just want to deliver value. So focus on that. Forget about the technology. It's not the most important thing. Now, Agile had a good start with this because in Agile, rather than having the whole waterfall thing, you have the domain experts or the on-site customer or whatever you want to call them, and the development team talk to each other, be in the same room as much as possible, really interact rather than being detached. And then the developer writes some code, and the code turns into a deliverable, and you get feedback from the domain expert as frequently as possible. So Agile is very good. It's all about fast feedback. But there is one little problem with Agile, which is that the code is often still a translation from the developer's head. So the code tends to be very developer-centric. Now, in domain-driven design, we solve this problem by trying to create a shared mental model that everyone involved in the product shares. It's shared. Everyone uses the product owners, subject matter experts, domain experts, on-site customer, whatever you want to call them. And in particular, this shared language is used in the code as well. Okay, so here we have our code. It is not a translation from the developer's mental model into code. It is the same code. It's the same mental model as the domain experts are using. So ideally, the domain experts can look at your code and give you feedback on it, because it's the same. They're using the same words in your code that they're used to using. And it becomes sort of documentation as well. So there you go. Your shared language is in the code. So this is an approach that I think is really good for doing design. We have the contribution from Agile, which is you rapid feedback. The domain-driven design side is you have this shared mental model, and you have the code also represent the shared mental model. So if you do that, and when I've done this kind of thing, projects tend to be quite successful. So communicate the design in the code is a key domain-driven principle. Now, at this point, a lot of you are probably saying, yeah, that's nice in theory, but can you actually make the code represent the domain? Is that even possible? Because this is what source code looks like. We all know this is what source code looks like. I mean, even the person who wrote this couldn't understand this way. So this is what people think source code looks like. So let me show you what I think source code should look like. Now, what you have to do is you have to guess what domain this is. This is F# code, by the way. You have to guess what domain it is and what the various concepts are, and what the key concepts, what the shared language is. Okay. Well, I think it's pretty obvious. It's something to do with cards, because it says card game right at the top. These words down the side, the suit and the rank and the thing, this is the shared language of the domain. And they're right in front of you. So if I'm a new developer, I'm coming onto this project and I don't know anything about cards, which is, let's say, if I just look at this code, I can already have a good idea of what's important in the domain. I don't have to go to 20 different files. It's like staring me in the face. That's very nice. So you can actually get feedback from non-developers. I mean, I say to the non-developers, I say, a vertical bar means a choice, and that little star means a pair, and that means a list. And every time you see the arrow, I call these actions or workflows, right? So let me just go into that a bit. So I'm going to go modeling workflows with a function. So to deal some cards, you start off with a deck. You have a deck in your hand, and after you've dealt a card on the table, you now have a card on the table, and you have in functional programming, things are immutable. So you can't change the deck. You can't mutate the deck. What you have to do is make a clone of that deck with that card missing. So you have a copy of the deck, or a version of that deck without that card anymore. So that's the output, is a new deck and a card on the table. So we can model this in a functional way, saying, well, the input is a deck, and the output is a pair. You have your deck and you have the card on the table. And again, if you want to pick up a card from the table, the input is the hand that I have, and there's a card on the table. That's everything I need to do this function. And if I needed something else, that would be another parameter. And then after I've picked up the card on the table is missing, and it's no longer there, and I have a new version of my hand. Again, I can't mutate my hand. I have to make a copy of the hand with this new card added. So that's how you would model picking up a card. The input, there's two parameters in the input, and there's one parameter on the output, or one thing on the output. Okay, so here's our domain. Do you think this is a reasonable amount of code to write to capture a domain? I think yes. It fits on one page, which is really nice. In practice, you think, well, this is a simple domain, but I've worked on really complicated domains like tax, and 4 or 5 pages maybe, and this is just like one slide. It's amazing. The process of doing this is actually a great way to get everyone on the same page in a business. Often you have people who are different teams, and they actually don't even communicate, and doing this actually forces them to get them all on the same page. Do you think a non-programmer could understand this? So when I was doing a workshop, and I was like typing this up, somebody said, some of the product manager, not a developer, said, well, this is great, this is really nice documentation, but where's the code? And it's not really obvious that this is actually compilable code, which is kind of cool. Do you think non-programmers could provide useful feedback to this? So there is actually a deliberate mistake. Anyone see what the mistake is?
Ace missing.
Ace is missing, there you go. Very good. Now, if you're a non-programmer, I think you could still give that feedback. I mean, again, in my experience, like if there's some kind of complicated cases, they can provide information you forgot to handle this particular case. Because there's no code, there's no implementation here. This is kind of, you might think of it as designing the interface for the domain. So there's a reason why it's called domain-driven, because it's not database-driven. Right? There's no foreign keys, there's no joins, there's no tables or anything. It's all about the domain. Everything here is about the domain. And the domain-driven design people call this persistence ignorance, meaning you don't know anything about how this gets stored. Now, obviously, in a real app, you do have to store this somewhere in a database or a file or whatever, but that's not part of the domain. That logic of how you store something, is important. It's part of the implementation, but it's not part of the domain logic, right? So it's important to keep them separate. Also, it's not OO-driven. There are no base classes, there are no manager classes, no factories. If you have two different concepts, like a hand and a deck, they might have the same representation as a list of cards, but you model them as something completely different. You don't have a base class that they both inherit from. Right? That's not how the real world works. So in the real world, you have these words, these concepts, and in the code, you have the same concepts. That's domain-driven design. So the domain has to be in sync with the real world. Right? There's no translation. You're not translating what the experts think into your code. You try and use exactly the same words. So that's the right way of doing it. Now, what you shouldn't do is use any kind of programmer jargon. Let's say you need something to manage all these different players. So you have a player controller or a player manager. And then you say, well, the deck and the hand are similar, so let's create a base class. And let's create an abstract card, proxy, factory bean, or something. Like, these words do not belong in the domain. Right? Now, they may... In the implementation, obviously, the implementation can get tricky, but in the domain side of things, the interface side of things, they should not exist. Okay, so if you see those kinds of words in your domain, you're doing it wrong. So what I like about this is the design and the code are the same thing. Typically, this is the first file in like an F# project, and the rest of the code has to conform to this. So this is the design, is sort of the interface for the rest of the code that has to implement it. But it always stays in sync. You never have this problem where a UML diagram is out of sync or a Word document is out of sync. The code and the design are the same thing. So this is executable code, this is not pseudocode. Right, so communicating the design and the code is one of the key principles, and I think we did that quite nicely. Right, so there's one other thing I want to talk about in domain-driven design. There's lots and lots of jargon, unfortunately, in domain-driven design. If you read the Blue Book, sadly, there's a lot of jargon, and there really shouldn't be jargon because it's meant to be user-friendly. But there is a useful concept called bounded contexts. And I think it's an extremely useful concept for us to think about. When you're implementing something in your domain model or your code, there's naturally kind of areas of things where there's similar functionality. Like if you've got an e-commerce site, there's an order-taking part, and there's a shipping part, there's a billing part, whatever. So the DDD people call these components a bounded context. And it's really, really important to think about what these things are and how they are defined. The boundaries are very important. That's why they're called bounded contexts. So a context, right, means a specialized piece of knowledge, common language within that area. And if you take it out of context, it means something different or it's unusable. And I've seen situations where often you try and have maybe a company-wide project to define what a customer is. And the marketing people have a definition of a customer, and the billing people, the finance people have a definition of a customer. And they're incompatible definitions because, they may use the same word, but they're different. Marketing people, it's all about spamming you, and billing, finance people, it's all about, owing you money and stuff. They're just very different. So just because they use the same word doesn't mean it's the same thing. So the context is really important. And it's just, be very aware to try and have a global context that everything fits into. Normally in a business, there's specialized context. And if you take it out of that context, you end up in trouble. And the boundaries are very important. Just like with human relations between software components need to have boundaries. Otherwise, you're in trouble. And one of the reasons for having boundaries is to make them autonomous. Because if you don't have a boundary and everything's kind of mushed together, you're always frightened that if you change something over here, it's going to break something over here. And if you have a boundary, a wall between them, you can freely change this bit and not have to worry about the other bit changes. It's a bit like if you're running a three-legged race, if you're tied to somebody at the ankle or something, it's really hard to run. Even if you're the world's best athlete, you're still not going to run very fast. If you separate people so they can run independently, they'll do much better. So boundaries keep you focused and they stop you doing scope creep. Really, really important. So here's a bounded context. And we're going to model our workflows as little things in our bounded context. So bounded context is really, from our modeling point of view, just a set of related workflows. Things which belong together because they have something in common. They use the same vocabulary, they use the same terminology. Now, if you have a workflow that doesn't belong in this bounded context, well, you stick it in another one, and it's really easy to do because there's no dependencies. They're standalone things, right? Because we're implementing workflows as functions. So they're really easy to move around. It's really easy to refactor if you make a mistake. Right, so we're finally ready to reinvent the transaction script. So we're going to take two parts. The functional programming part is to implement transactions as functions, and then we're going to build them from components using composition. So rather than just having a big mass of stuff in a big file, we can break it down into little pieces and build them up from composition. Now, what's interesting about that is if you break it into, let's say you have a little component in your thing, and you only use it in this one transaction script. That's fine, it's not a problem. But if you ever do want to use it in another transaction script, because the functions are standalone, because all the parameters are passed in, because they have no dependencies on global state, it's really easy to reuse functions in different contexts. Now, the functional domain modeling contribution, which I just showed you, is using composable types to create a rich domain model. Now, we said at the beginning that one of the problems with transaction scripts is they don't have a rich domain model. It's just a bunch of strings and ints and database calls. So if you do this nice domain modeling thing, you can actually get these really nice composable types. Yet, the individual actions are still standalone. If you have an object-oriented domain model, where you have a lot of objects and they all talk to each other, it's really hard to pull out the individual methods because everything's sort of tangled up. But in this kind of functional domain model, you can still have the rich domain model, but the individual actions, because they're modeled as functions, again, they are standalone things, and you can refactor them, pull them out, put them somewhere else much more easily. And again, we're going to steal this idea of bounded context as a way of grouping and managing the workflows. So everything in a particular bounded context has the same kind of context, the same vocabulary. Right, so let's go and look at the pros and cons that I talked about at the very beginning. I said one of the pros about transaction scripts, they're really easy to understand, and they're super focused because everything in them is relevant. That's good. And then I said some of the cons were they are hard to modify, hard to evolve, hard to reuse. There wasn't a rich domain model, and they were hard to test. So all these downsides. So I think this is one of the reasons why transaction scripts have become out of fashion. But let's see if we can solve all these problems. So I'm going to make a number of claims. This is what I personally think. Of course, just like unfortunately, given that software is like $1 trillion business, we have so little hard evidence for anything. It's really shocking, actually. I'd be quite happy to have double-blind tests for all this stuff. But literally, people just make stuff up. And this is the kind of conference where people do make stuff up and say it's my way is the best way of doing something. So that's exactly what I'm going to say. I'm going to say my way is the best way of doing something. So I'm going to claim that doing this approach is really good. So I'm going to say, first of all, that the functional style transaction scripts are actually easier to comprehend than an object model. Okay. So here is a functional pipeline, a transaction script. All the arrows go left to right. There are no backward arrows. Makes it much. I think that's really, really. I mean, people really underestimate how important this is. I think it makes it really easy to understand. And again, if you have a whole web framework or something, a whole web app implemented as a function, you can always follow the data through left to right. And I can't stress how easy that makes debugging. So even with the branches, there's branches, but the branches all go in the same direction. So that's awesome. Now, in an object-oriented workflow, you have this kind of request-response model, not input-output, but request-response. So there's a particular object I send a request to, and I get a response from them. That object will then talk to somebody else. That object will then talk to somebody else, who will talk to somebody else, who will talk to somebody else. And there may be a little bit of back and forth. And eventually they go back to the main object, and the main object gives me back the response that I asked for. And it's easy to accidentally make this very complex. Now, if you do it right, just to you know, I mean, I'm not hating on OO because I actually used to do a lot of small talk, and small talk is awesome. And if you do it right, it's very nice. But it's very, very easy to make stuff overly complex. Because the arrows go in all directions. Trying to chase down where you're going can be really hard. Now, what's interesting, when we do microservices, we do not design microservices this way. If you saw a microservice that talked to another microservice, which then talked to the original microservice, which talked to a third microservice, that would be considered bad design. Right? That would be a really bad anti-pattern for microservice design. And yet we design OO stuff that way. So I would take the same principles and apply them to OO design to try and have a linear, one-directional model. Now, this is a graph that I built myself by analyzing the dependencies in a C# project. And there are easily a couple of hundred classes. Every little line is a dependency from one class to another class, meaning that class referenced that other class. And what you can't see, first of all, you can see it's really complicated. And what you can't see is that the arrows go in all directions, and you actually get cyclic dependencies. Now, cyclic dependencies are evil. I have a whole talk about that. They're really, really evil because they're all tied together. You can't pull a piece out because it depends on another piece, which depends on another piece. Literally, when you do that, you have no more layering. You have no more top to bottom. They're all in one layer. Everything that depends on each other in a circle, you might as well make it one object because you're not getting any benefit. So now this is interesting. This is an F# project. So this is C# and F#, so the same .NET underneath. The F# project basically has exactly the same functionality, but as you can see, there are a lot less components in it. And what you can't also see is that all the arrows are going left to right. So even if you, if you zoom in, you can actually follow the code all the way through. So yes, there's, some pieces have big dependencies, but there's a lot fewer than the OO stuff. So another claim I'm going to make is that FP style transactions are much more resistant to bloat. So here is an OO interface that I sort of seen. I'm going to call I repository. And it's got an insert method, and then later on they've added an insert async method, and then later on they added another one, a delete method and a delete async, and an update async, and then maybe a commit changes so they can support something else, and then commit changes async because that's a new thing they need support. And then there's some way of querying, but then maybe you want to query by key, and you query by a filter, and then you query by some sort of specification object. And then you want to optimize it because the SQL is too slow, so you write a contains method. And then you want to optimize that too, so you have a count method. And then you want to realize that you're pulling too much back from the data, so you have a summary record that you pull back instead of all of it. And then you need a version 2 of that summary record because you need to be back compatible with the previous one. Oh, and by the way, let's change the customer password while we're at it. Oh, and let's have a backward version of that too, version 2 of the password. And let's accidentally, for admin purposes, for testing purposes, let's have a method called delete all rows in the database. Well, that's great because that could never possibly go wrong. That would never be missed. And accidentally, you're only supposed to use it in the test environment. Just promise me you'll never accidentally call it in the production environment. And then here's a launch missiles because we really want to cover every possible thing. And of course, you need to backward compatible launch missiles version 2. So this is the kind of thing that obviously this is kind of silly, but I have seen interfaces with like 30, 40 methods on it, right? So what the problem is here is that you have this interface that's trying to support every possible workflow, right? It's trying to support all the possible things you could do with a customer or whatever it is here. You're trying to, maybe you want to insert it, maybe you want to delete it, maybe you want to change the password, maybe you want to launch the missiles, I don't know. But you're trying to support it all in one interface. And we have the whole principle in OO design, the interface segregation principle, don't do that. Don't make people depend on things they don't use. But even though we have this principle, it still happens anyway, because there's a kind of natural entropy where things kind of get bigger and bigger. It's just easy to stick it in another class, or another interface, rather than making a whole new thing. So, I think Jeff Goldblum had it here, don't just do it just because you can do it. Think about whether you should do it. Now, one of the nice things about the functional thing is that you don't have bloat, because a transaction script only has what it needs to do its job. It's really hard to have bloat, because why would you even bother to write a method that's not needed for this transaction script? You wouldn't even bother. Now, if another transaction script needs another method, we'll write it in that one, but don't write it in this one. This one, they tend to be very, very focused, very, very isolated on these things. They only need what they need. So you don't need to have things like interface segregation principle and Yagni and all that stuff, because it kind of, there's a natural tendency, there's the pit of success, you fall down into not doing something rather than having to be reminded to do it. So that's kind of nice. So every part in a transaction script tends to be relevant. You get the interface segregation principle sort of for free. And if you do want to remove something, let's say you see something's no longer relevant, you can remove it because these are autonomous. If I remove it from this transaction script, I guarantee I haven't broken anything else, right? Because unlike if I remove a method from a class, who knows what people you're depending on that method, So you have to follow all the users of the method, and et cetera, et cetera. So, right, another claim I'm going to have, which is that you can modify these things with confidence. Now, again, if you look at the COBOL code or the Java code or the Python kind of transaction scripts, you often are very worried about modifying things. But here is a version 1 of the workflow, and then I'm going to replace that component with version 2. Now, I feel confident about that for a couple of reasons. First of all, when I replace a piece of the pipeline, I haven't touched the rest of the code. I'm just replacing that one piece. So I'm a lot more confident than trying to mess with a lot of code. I'm just messing with one little piece. That's good. And the other thing is the inputs and outputs. If I'm using a statically typed language, the compiler will make sure that the inputs and outputs still match. So, for example, if I'm dealing with a deck or something, and I have a new version, it still needs to take a deck as input. It has to have the same inputs and the same output. So it's going to have very, very similar functionalities, much less likely to kind of get it wrong. Now, if I want to add features to a workflow, it's really easy. I just stick a new thing in the pipeline. And again, I'm minimizing the amount of code I have to write. I don't have to touch any existing code. I just stick a new thing in the pipeline. As long as the inputs and outputs match up with the types, I have very high confidence it's going to work. If you need to do branching, again, I can just do some sort of conditional and branch on these two things. And if the branching gets really, really complicated, I just have a component, again, just like a dispatcher or router or whatever, that figures out what's the input and immediately calls one of these 20 other functions. But the individual functions stay very small and isolated. So the actual choice, the decision making, gets separate from the logic. So it tends to be simpler to work with. And of course, another common problem is you have two workflows and they're almost exactly the same except for one tiny little thing which is different. So rather than copying and pasting the whole thing, you just want to parameterize it with that one little parameter, whatever it is. And here is an example. You have a workflow, it's got a slot in it, and it's parameterized, and you pass in the thing that you need. Now, that thing that you pass in, it could be a constant, a number, but it could also be a function. It could be the strategy pattern. You pass in a function to decide exactly how it behaves. So again, you have a very high confidence that this is going to work because the types match up. All right, now what about this rich domain model that transaction scripts don't have? So here is our two functions from our card game model. And if you see these things, we're using words like deck and hand and player and stuff. We're not using ints and strings. This is a rich domain model, right? Now, the fact we've implemented them as functions, it means that we get the benefits of both. The domain model is used in these functions or these transactions, but the functions are independent, so I can swap things out and swap things in without breaking something else. So all the nice things about a rich domain model without having things being tangled up where you can't change stuff without worrying about it. And if you want to share a component, let's say I've built this function that does a deal, and it has a deck as input, whatever, and I want to reuse this component in multiple places. It's a very useful component. Well, I can just use it in all these places. I don't have to create an interface, so I don't have to retro-engineer something. Every function is automatically an interface. Any function that takes in a deck and spits out a new deck or whatever will fit in this slot. So it's actually very easy to reuse things without having to retroactively refactor things. And again, I have a high confidence that it will fit nicely. So shared components with rich domain logic is actually quite easy to do in this approach. So it is compatible. People say either you have to choose between transaction script, which is kind of boring, and a rich domain model, which is sophisticated. And I'm saying that you can actually get the best of both worlds. You can have a nice rich domain model, which is super complicated with super complicated business rules, and still assemble transactions in a linear way, which are easy to understand, which don't have any extra cruft in them, still using this nice rich domain model. So the best of both worlds. People who are, when the whole layered architecture first came around, people realized pretty quickly that there were some issues, and the onion architecture and the clean architecture and the hexagonal architecture, ports and adapters, all these variants of that started evolving. And I'm going to show you how this evolves naturally from functions. So here is a classic layered model, layered architecture, with an API layer and a services layer and a domain layer and a database layer, and some workflow comes in from the API and it comes all the way back out to the API and so on. Now, one of the reasons this is a bad approach is because if you need to touch one of those workflows, if you need to add a field to the customer or whatever, you have to touch every single layer. And that really goes against the principle, code that changes together should live together. If you have to change 4 different things in 4 different places, that's actually a really bad way of organizing code. So a much better way of organizing code is in vertical slices rather than horizontal slices. And I think you see quite a few people talking about this approach. And if you want to change one particular workflow, all you have to do is change the bits that are relevant for that workflow, and you're not touching anybody else's workflow. So this is a much better way of doing it. Now, if you take these things and you kind of pull them out, stretch them out sideways, you end up with something like this. So something comes in at the API, and then it goes services, domain, hits the database in the middle. Notice the database is the center of the universe here. More domain stuff, more services and stuff. So this is how you do it if you stretch out one of these workflows into sort of a pipeline. And you can see it's kind of ugly. It's really confusing. You're doing things multiple times. This is bad. So the answer to this is onion architecture, or clean architecture, or ports and adapters, whatever. The idea is you have pure code in the middle, and you have all the infrastructure, or the API, or the database, or whatever, around the core. And that's it. Now, what's interesting is this is exactly what functional programming is all about. In functional programming, you separate the pure code, pure meaning deterministic, the deterministic code, which is all the business logic, but no I/O. And anything to do with interacting with the outside world, anything which is non-deterministic, is at the edges. So the functional programming and the kind of these kinds of architectures really are a match made in heaven, I think. It's just a natural way of doing things. So there's a talk, Functional Core Imperative Shell, which I'm sure some of you have seen. If you haven't checked that out, it's exactly the same thing. It's about having a pure core, deterministic core, which is easy to test, and an IOs at the edges. Right, what about testing these things? So I'm just going to review some of the key testing concepts. And I think I stole this from Ian here, because I think this thing about the system under test, and you can probably correct me if I'm wrong here. So the system under the test should be a unit of business value. Okay, so you should be testing business value, not just classes on their own. So what is the unit of business value in this idea? It's a transaction, right? Those are the things you should be testing. Don't test the individual classes. And you should test the boundaries. You shouldn't be testing the internals of things, because those things change, and you're going to have very brittle tests. So what is the thing that goes from one boundary to another boundary? A transaction. And then people think unit tests mean units equal classes. Unit is just a unit of functionality, right? And it's a unit of functionality that can be isolated and tested on its own without breaking anything else, which doesn't depend on anything else. So it's a unit of functionality, not a class equal unit. So I think that's right. Is that good? Yes. So Ian agrees. So that is the thing about testing. So notice that the transaction model of doing stuff really matches this really nicely. You test transactions, you don't test classes. So here is what a FP-style transaction script looks like. So you have this big function, but inside the big function there's a couple of pieces. There's a bit of I/O, there's your business logic, and then you have a bit more I/O at the end. So all the I/O is at the edges in a functional model. So typical things, you load some data from a database, you do some business logic, and you save it back to the database. I mean, 99% of transactions are like this. And if it's more complicated, you can make it a bit more complicated. That's basically it. Really, I would say almost everything is like this. Now, what's interesting is the business logic where you're making decisions is deterministic. It's normally, I have this piece of data, what should I do with it? You know, should I accept the payment, should I not accept the payment? All these branches and the conditionals and all that stuff, that is deterministic code. And that is where the complexity is in typical most business logic. It's like, it's complex, but it is deterministic. If I have this input, I guarantee to have this output. Now, anything to do with databases or files or the outside world is non-deterministic. So it's really hard to test that kind of stuff. But if you write your code in this way, with the I/O at the edges and the pure deterministic business logic in the middle, it's super easy to test. The testing falls out without even thinking about it, because the pure deterministic business logic is a unit test. It's pure. You can just like pass all the inputs in, do your test, and check that the outputs are right. It's always going to be the same output for the same input. Completely deterministic. Now, if you want to test the whole thing from end to end, that's an integration test. And that's where you have to hit the database or the file system or the network or whatever. That's fine. But this comes from this architecture, the difference between a unit test and integration test, like, it falls out naturally. And what you should be testing, you know, falls out naturally. You only have to test the business logic. You don't have to test a bunch of little classes and stuff. If you do need to do more complex I/O, you can do it in the middle of the workflow, but just keep your I/O separate from your business logic. Keep the deterministic stuff separate from the non-deterministic stuff. Right. And you can do front-end stuff, like you can do front-end style like this too. If you're used to the Elm architecture or Redux, the model view update architecture, where you have this message pump and you have an update thing and a render thing and you have a browser thing. These are all functions. The little update thing and the render thing, these are pure deterministic functions, which make them really easy to test. And all the I/O, all the non-deterministic stuff is in the browser or in the library that does this stuff. So this is a reason why people like doing this on the front end as well. Right, let's just finish up with some deployment options, because what's nice about this is you can actually get a bunch of, if you follow this approach, you're not tied down to running things on a mainframe using COBOL. You can actually do some cool things. So there's 3 different architectures which are sort of common use now. So monoliths, right, standard architecture. So in a monolith approach, each of our bounded contexts is going to become a module in our modular monolith. And because these bounded contexts are autonomous and they have well-defined boundaries and well-defined interfaces, we can still put them in a monolith, but they are modular. So that's good. Now, if you have a service-oriented architecture, each of these bounded contexts would typically be in a container. So a bunch of microservices or whatever in a single container. And if you're doing serverless, then each of these individual workflows become deployment units, right? You just deploy these individual workflows because they're stateless. Remember, they have the I/O and at the front and the I/O, but they're really easy to make into lambdas, whatever. So serverless works really well for this approach. So here's the modular monolith. So here are a couple of bounded contexts, 3 bounded contexts, and they have these workflows, but they're modular. Like, people say, well, I want to have, you know, how do I get modularity? I need to go to microservices. No, you don't. If you can't build a modular monolith, what makes you think you can build modular microservices, right? It's the same principles. This is a deployment thing. It's not about the design thing. You should always design things to be modular, no matter how you're deploying them. So modular monolith, there's the kind of boundary, that little red thing, that's the boundary of the deployment. And you can also have a split deployment where you have a front-end part and a back-end part, and they're really part of the same bounded context, but there's 2 little workflows, and they communicate with like an API. So that's one way of doing it. Now, if you're doing microservices or container-based stuff, you can each little context can be its own unit of deployment, like in a Docker container or whatever, I don't know, Kubernetes, whatever. For serverless, each of these individual workflows becomes something you deploy. And what's nice is that you can, if you've architected your stuff right, if you design your stuff right, you can switch between these different deployment approaches with minimal pain. I mean, there's always going to be pain, but you know, as long as you design your stuff to be modular, notice that everything here is completely modular. Right, so let's finish up. We have the reinvented transaction script. So going back to Martin Fowler's definition, business applications can be thought of as a series of transactions. We are going to organize it as a single function with a deterministic core and I/O at the edges. So it's no longer a procedure which mixes up database stuff. And each transaction will have its own autonomous, evolvable transaction script. I think transaction scripts should be more popular. So this is what the whole point of this talk is, because what's cool about them is they are very business focused. When you do something, it's just about getting stuff done. You're not worrying about which framework you should use. There are no frameworks in transaction script stuff, by the way. It's all libraries, but not frameworks. It's very business focused. It's actually really good for Agile, if you're doing Agile properly, because the transaction becomes the unit of development. It's like a story, a transaction and a story. It's like, this is what I'm going to do this week. I'm going to build this thing. And you're focused on delivering business value all the time. And it's really easy to understand because the data flow is one-directional. Right? So no bloat or less bloat. Of course, you're always going to have bloat because we're developers, but hopefully you have the forces working towards bloat are countered by the fact that these things are kind of small. And then all the problems that we had, we solved them with composability and putting the I/O separately. So for example, the new improved transaction scripts, they have a rich domain, unlike the original ones. They're easy to modify, unlike the original ones. They're super easy to test, unlike the original ones. And they're hipster-friendly. They work with microservices and serverless and all the latest cool kid stuff. So they're very cool. The new improved transaction scripts, definitely what the cool kids should be using today. So thanks very much. I'm going to post the slides and videos on my website there. If you like this kind of thing, I have my Power of Composition talk and my Domain Modeling Made Functional talk. I have a whole book about domain modeling. Please contact me on Twitter if you have any questions. And thank you very much.